All right, next up, we have Dr. Paul Swinton from the Robert Gordon University. Paul is close colleague, good friend, and my go-to guy for all things statistical and methodological. And I think these two talks, James, who we just heard, and Paul's, who's now going to talk about simulation, really do align very closely. So I think this is going to be another super interesting one. And Paul, over to you. Thank you very much.
Thanks, Emer. Is that my screen sharing?
Yep, looks good to me. Sounds good.
Excellent. Okay, perfect. Thank you very much for the introduction. And yeah, I think hopefully this talk follows on nicely from James. So I'm going to expand and go into more depth on computer simulation modeling, and sort of like James sort of identified, sort of explain why I think this is a underappreciated tool for conducting research and shaping practice in sport and exercise science. So in this session, I'll introduce computer simulation modeling, or CSM for short, define terminology, and discuss some of the potential uses and strengths in sport and exercise science. To provide context, I'll provide quite a few different examples so people can see how CSM works in practice, but I'll focus predominantly on modeling the athlete response to physical training. So again, that fits quite nicely with some of the stuff James was talking about with regards to not just looking at do things increase, but how do you think about that in more complex modeling terms. Finally, I'll end the session with a comparison of traditional research approaches and a CSM approach to address a complex question and show how they're quite different in terms of the creativity and sort of thinking that goes behind them. So another good thing that highlighted by James' talk was differences in terminology. So just to confuse people, I'll use quite different terminology than from what James did, but that's fine. Terminology in modeling and simulation is highly discipline specific and can even change across sub-disciplines. But I think what's important is that you define your terms, and hopefully differences among the constructs are clear. So in terms of the terminology I'll be using, I like to think of CSM in terms of a hierarchical flow. So first we start with our system, which is effectively, for me, a simplified representation of the entities and processes that are to be investigated. So basically what that means is we're going to highlight the features that we will attempt to model and those that we're ignoring. It will also highlight in your system the detail that will be used to model the different elements of our system. So for example, we may choose to have a system comprising an athlete, their equipment, and the environment. So the athlete we may choose to represent by their fitness capacity. The equipment may be by, say, something like a bike and its ability to convert metabolic to mechanical energy. And the environment, which consists of potentially factors like air resistance, temperature, and the gradient of a hill. Another system might be an athlete training system, where the athlete is represented by their antagonist response to exercise, so their fitness and fatigue responses. And training might be represented by, a numerical representation in terms of a time series, which quantifies the training dose. And either that could be a scalar, so a single number, or potentially a vector. That vector might be something like intensity, volume, frequency, and so on. Other examples of systems include in team sports, we may be interested in the interaction between players, such as dyads, and a fruitful area of CSM, which I'll talk about a couple of times in this talk, is performer and measurement error systems. And there's a good reason why measurement error tends to fit well within CSM. So once we have our system comprising the elements and processes that we're interested, we then want to develop our model. And our model contains two components. So the analytic component that basically expresses the interrelationships between our components in the system. And that will specify things like the relationships. Are the analytical relationships, are they linear, non-linear? Are they delayed or not? And then we also have the descriptive component. So for each of the elements in our model, in our system, we would like to describe them mathematically. So that will involve potentially more deterministic equations. If we're trying to represent physical laws, that happens quite a lot in things in areas like biomechanics. Or, for example, they may be relational, expressed in terms of differential equations like they are in fitness fatigue models, or they may involve probability distributions. So in our previous example of the athlete equipment environment system, we may choose in terms of the analytic to have the environment influence both the athlete and the bike. And then as we move down to our components, we may choose to model the athlete as some sort of tank with capacity that drains as time goes on. The rate might be influenced by the intensity of the activity and the temperature in the environment. And for example, we may choose to model the bike of different qualities that are either more or less effective at translating the energy flow from metabolic to mechanical. And that capacity may be influenced by air resistance, for example. A different example, we may have an athlete training system with just a single arrow from training to athlete. Or for the analytic component, we may try to model some sort of feedback process where the training influences the athlete, but then that goes back and then requires a manipulation to the training. For different athletes, we would create distinct fitness and fatigue profiles, and again, I'll get into that in the next couple of slides. We may choose to model different asymptotic values based on genetic limits and so forth. But kind of going back to what James said, in general, what will be important when we are formalizing, if you like, the descriptive part of the model, that will involve us deciding on functions and parameter values. And ultimately, they'll need to be estimated or elicited from experts. So we started off with the system, we then had our model. So in the CSM framework, finally, we have our simulation. And a simulation is simply an execution of the system and the model developed. Computer simulations are conducted in a computer involving code. So this is an example of a simulation that we've run in the past in terms of fitness and fatigue models. You don't have to sort of go through the thing line by line, but just to give you an example of actually how it's done in practice. In your code, first you'll set up your system, then you define your model in terms of functions and parameters. And then generally in a simulation, we perform some loop that performs the simulations for thousands and thousands of iterations, each one collecting values that provide information on our system. In terms of a CSM study, typically what we do is manipulate some independent variable or a starting point, and we see basically what effect this manipulation has on the distribution of the values across our simulations. So that's a basic overview of CSM. What I'd like to do is now go on and give quite a few examples just to provide more context. So in sport and exercise science, CSM was studied originally and most extensively in biomechanics, where models are governed by physical laws that can be created. So in this example from Untitled 2000, a CSM was used to investigate how to minimize peak force at the shoulder of a gymnast performing swings. So in the CSM, the system comprises the athletes in rings. As we move down our hierarchical flow, we then move on to the model. So the athlete is modeled as a set of 5 rigid bodies with elastic components at the shoulder, hand, and at the anchor points of the rings. We then use forward dynamics to create a system of equations between the angles of the segments and the rings. And then the clever part of this is those models involve parameters, and we select those parameters so that our simulation matches the data obtained empirically from each athlete. So in other words, we can fit the model to each athlete depending on their different anthropometrics and so on. The simulation can then be used to manipulate, for example, different techniques and postures to identify which postures result in the lowest peak force. So that's an interesting example of CSM where we use physical laws to set up our model. Another popular area of CSM in sport and exercise science, and the one I'll focus on primarily in this session, is modeling of training response. So this initial system was proposed by Calvert and Bannister in the 1970s. They considered a systems model where performance in sport was determined by four main components, including cardiovascular endurance, strength, and skill, which were all influenced by a training input. And performance in the sport was then modulated by psychological components that they summarized by the athlete's drive. So for the system, in terms of a model, what's interesting is, in terms of when you're specifying your system, is that the absence of links represent just as strong assumptions as the presence of links. So for example, in the system, strength, there's no arrow from strength to skill. So in our system, we're basically stating that these two things, there's no interaction between them. You know, when you define your system, it's not just the components, it's how effectively they relate to each other, whether they're independent or not. So Calvert and Bannister identified that, you know, whilst this is somewhat complex, it's still a very simple model given ultimately what you would need to explain performance in sport. But they chose to focus on a single component such as strength and sort of show how you can model this in more detail. So this is their sort of, if you like, famous fitness and fatigue model. So how they came up with this is they basically argued that if you went to a practitioner and asked them, describe what would happen if an athlete suddenly increased their training by a moderate amount. They argued that most scientists and practitioners would say, well, if you increase the amount of training, what would happen is performance would rise to a limit after about 30 to 50 days. A further increase in training would cause a further rise in performance, but that would most likely be proportional to the difference between a maximum performance and the present performance. And if someone stopped training altogether, basically what would happen is that performance would return to its initial level. Now, that behavior is well described by a simple first order differential equation. So that's how they chose to model it. But they also said, to be a bit more realistic, what we could do is not just have a positive effect, but we could also add in a negative fatigue effect from training. And again, they described that by a first order differential equation. So you've got performance, which is equal to some change in performance, which is equal to some initial performance level plus two first order differential equation. So you can solve that system or approximate the integral, and you end up getting this sum of exponentials. And it has four parameters that you can use to fit to an individual athlete. So you've got your gain coefficients. Those are the K values. And basically what they do is they determine the magnitude of the fitness and fatigue effect. And you've also got time coefficients. So that's the tau values. And they describe how quickly the fitness and fatigue response fall to zero. So in fitness and fatigue modeling, what we try to do is develop parameters that describe the response of an individual athlete to training. And once we have those parameters, we can then perform simulations. So a common simulation approach is to take our parameters in a new training program and predict how the athlete would respond to that training program. And obviously, if a coach maybe has multiple training programs that they're considering, performing the simulation may assist in them determining which program they're ultimately going to select. Also, we might be able to use fitness and fatigue modeling to identify when you structure or perform your last training sessions so that you peak at the appropriate time. So there are a number of potential advantages of conducting CSM research. The first, definitely, as James said as well, is that when you try to create a CSM, you're forced to explicitly state your system and specify analytic and descriptional aspects of the model. And that really requires deep thinking about the area. Also, in order to perform a CSM, you have to estimate parameter values. So again, it helps you work out what areas of research you've kind of got good information, and which areas you really don't know anything. So if you're not able to come up with an analytical process, describe how things work, or come up with any parameter values, then it's clear that there's a lack of understanding in the discipline. Secondly, in an ideal world, what we would like to do is derive closed form analytical solutions. However, typically that's only possible when dealing with toy examples. So in order to keep problems tractable and also contextualize them in an applied framework, CSM tends to work better rather than going down sort of closed form solutions. Third, CSM can be used to provide insights when other research approaches, including experimentation, is too costly or unethical. This is routinely the case when considering elite athletes, for example, and where it might not be ethical to manipulate their training. So CSM can provide some initial insights. Fourth, simulation provides one of the rare cases where researchers, quote unquote, know the truth. So in the sense that when you perform you have the simple, the limitations of a simulation being a simplification of a system, but it's the one time where you have the parameter values and you know what the dependent variable is, so you can see the effects of manipulating dependent variables. And I'll come back to that. Provides unique insight when working with measurement error models. As part of a program of research, CSM can enhance the overall output. If it's performed upstream, it can be used, for example, to refine subsequent experimental research, perhaps ruling out interventions that are less likely to work, or identifying what's the minimum requirements for a study to work. And I'll give an example of that in the following section. Alternatively, CSM can be performed downstream of, for example, experimental research, helping to move from translation, translate experimental results to practice, perhaps identifying how best to roll out a system or make effective use of resources and logistics to maximize cost effectiveness. So, as I said, measurement error systems fit well with CSM and sports science. So a large hurdle that tends to exist in many research areas of sport and exercise science is small sample sizes and large measurement error. So even when we perform empirical research, the underlying value of interest, that is the true value, may be quite different from what we observe. In contrast, the advantage of CSM is that we can, quote unquote, know the true value and simply add error on top to mimic our model of reality. As part of the modeling process, we can select various distributions for our errors. So we don't have to assume that errors are Gaussian, and instead we can select from skew distributions, which are potentially more likely to occur in things like maximum tests, where we have a skew and we're more likely to get large negative errors, and that would be due to things like injury or a lack of motivation. We can also make more complex error models. So for example, we can model the underlying structure. So perhaps we can assume that observations that are made closer together in time have a stronger association and so on. Again, those are quite simple things that we can do in our simulation. Using various error models, we can use CSM to identify minimum requirements such as sample size, or the number of observations. So perhaps we're moving, away from a pre-post, and we might have a opportunity to collect data on a weekly basis. So that obviously greatly increases potentially the amount of power we have and the ability to not just look at, did things improve, but are they linear, non-linear, and so forth. So if we employ a CSM approach, we can identify how many observations do we need to make in order to have sufficient power to capture, for example, a quadratic or some sort of cubic function. So what I'll do is I'll give some very specific examples from our actual CSM research. The first example that I'll give is in fitting fitness fatigue models and working out how they perform under different measurement frequencies and measurement errors. But before I do that, I'll briefly explain in a bit more depth how fitness fatigue modeling actually works in practice. So what happens is we start with a training program that an athlete would conduct, and we can convert that training program to a time series with, for example, a scalar representing the training stimulus for each session. So basically, a relatively large number will represent greater fitness and fatigue. So immediately you can see that this is quite a complex process. So taking a training program and boiling that down to a single number or perhaps a vector is a complicated problem. And you could imagine lots of CSM work that could be done just to tackle this one area. However, once we have our measurement process in terms of translating training to a number, we then perform the exercise. And what we need to do is we need to then measure performance. So perhaps we measure something like vertical jump performance or maybe force production. And ideally, we probably want to measure this somewhat regularly, although the purpose of the CSM is to assess how frequently we should do this. So once we have our training and we have our measurement, what we then do is we select a fitness fatigue model. And there are a large number of potential models, but this is the most basic one. So we can see that it provides an input for our training values here. So the omegas are the training values. And so each day that we perform training, that gets fed into our model. The fitting of the fitness fatigue model is achieved by selecting these 4 parameter values, as I said sort of earlier. What that helps us transform the time series of the training into an output of fitted values. So in this image, what we can do is we can see the observed performance values. So that's the round circles. And the green lines are the generated fit from different sets of parameter values. So for each set of parameter values, they combine the time series input and produce a time series output that we can compare with what we actually observed. So you can see some horrible fits. So if you see at the very beginning, you've got these green lines that are far from the observed values. And these are unlikely to represent the athlete as a system and how they respond to performance. So what we do is we obtain the best parameters. And typically how we do that is just an optimization step. So we have some cost function that we choose to minimize. And typically that might be something like the sum of squared residuals. And so what we have is a model building phase where we obtain our parameters by minimizing the distance between fit and observed. And then once we have those parameters, as I said earlier, we can then feed in a new training program and we can predict what will happen. So now that hopefully the process of fitting fitness fatigue models is a little bit more clear, I can introduce the actual CSM work. And so here what we're trying to do is determine the absolute minimum requirements with regards to measurement error and measurement frequency. So the reason this type of research works well is the fact that it can answer the specific question, which is, in a world where fitness fatigue model accurately describes the training response of an athlete, what measurement error and frequency would you need so that you could obtain suitable parameters in future predictions? So this shows the workflow of the CSM. So first we develop representative training programs and parameters so that the change over time represents what we typically observe in practice. So in other words, athletes may make about a 5% improvement over a 16-week training period. We then generate performance values according to the fitness fatigue model and the selected parameters. We then split the performance values into a model building block and a model prediction block, assuming that these values are true. Just as you would have in our real world model, measurement errors then added on top. In the simulation, many different measurement frequencies and error magnitudes are selected. So we are mimicking different measurement schedules. So for example, what happens if we measure performance every day down to once per week, and also different measurement systems. So measuring, for example, very accurate technology with 2% coefficient of variation, all the way down to cheaper, less accurate systems that maybe have up to 10% coefficient of variation. For each simulation, we take the data with noise and perform parameter estimation. With these estimated parameters, we can compare these to the true parameters and also with model prediction. So that's the last point, is that sort of comparison. Now, again, it's important to point out that you can only ever compare to the truth in CSM because that's the only situation where you can know the true parameter values for an athlete. So 2 months of running this simulation, that's partly because I'm not the best coder in the world. You can see that even in the very unlikely case, so this is the most idealistic scenario where a fitness fatigue model that we've selected is correct. So in other words, our theory is actually correct and specifies the response to training. This simulation has shown that if you have a measurement error of, for example, 10% coefficient of variation, then you will not obtain good predictions on average. So basically, if this shows you that if you don't have good measurement error, so for example, 4% coefficient of variation, then no matter what experimental research you do in the real world, you won't get to work because you're above, below the threshold required to obtain reasonable data. Just to highlight the fact that once you start the CSM approach, there are a number of spin-offs you can do. One such example that we've done is in parameter estimation. So it's an area that's been skirted over in most fitness fatigue modeling research. So researchers don't tend to provide much detail on the algorithms and processes that they use. So this is, for example, a schematic showing what an optimization floor might look like with just 2 parameters. So when we're performing parameter estimation, what we're trying to do is find the global maximum, so the highest point. When you move to from 2 parameters to 4 parameters, or maybe even up to 10 parameters, what you end up is getting a really, really complex optimization space. And it's really easy to get stuck on local maxima rather than find the global maximum, which we kind of want to do when we're performing fitness and fatigue modeling. So again, this is a really, really easy thing to do with CSM because we know the truth. So what we can do is we can go across a number of different algorithms and with realistic parameters, we can create simulations and see which processes and algorithms work well and under what considerations. So again, that will help researchers when they conduct real research in the field or real experimental research. They'll know what type of algorithms to use. So one last example, quite a different example, but I think it's an interesting one with regards to measurement error. This is a study. This is from a study we recently conducted looking at trying to quantify reliability of spatial temporal metrics. So that's something that's used in soccer, whereby you take positional data from individual players and try to work out metrics that describe how the team is functioning. So for example, this one here, you can work out Veroni cells and you can work out hulls and so forth to work out how the team are performing in terms of their shape and their communication. So we have lots of information that tell us how accurate the individual positional values are. So for example, we know from simple reliability studies that GPS has, a positional errors maybe ranging from 20 to 40, maybe from 50 centimeters all the way up to 4 meters. But what we don't know is how do those positional errors from individual players sum up and influence the reliability of complex metrics. And that's something that we were able to sort of address with a CSM approach. So what we did is we started with real positional data collected from players during elite international matches. And using this data, we calculated a range of popular spatial temporal metrics, including surface area, space control, and so on. What we then did is we added positional errors on top of that. So mimicking excellent technology of 0.5 meters up to poor technology of sort of 4 meters. We then used those errors and added them on top of 1,000 new matches. So for each each game that we actually had, we simulated 1,000 new matches with error. And then over 1, 5, and 15-minute intervals, we calculated the variation in the metrics, both in the actual data. So in other words, that's the within variation that gives us an idea of the signal. And we compared that to the variation across the simulations, so with the error, and that gave us our between variation, so our noise. And then it's really simple to calculate reliability. You just take the ratio, so the between variation relative to the total variation, and either, it's up near 1, so you've got almost no error and high reliability, or it's down at 0. And what we were able to show is that if you have very accurate positional data, then all metrics are fine. However, if you're using systems that maybe have error, like for example, up to 4 meters, then a number of metrics are likely to have low reliability, and you would ultimately then question their use in practice. So again, this is quite a good way to, you could theoretically have developed reliability by doing some quite advanced mathematics. That would have been quite hard to obtain things in closed form, but it's relatively easy to do so with CSM. Okay, so last thing I'd like to do is just compare a traditional research approach to a CSM approach in trying to address a very different but complex question. So this is something that I've been thinking about for a while in sort of trying to address. And so the question is, how important is physical fitness and soccer performance? And so there are probably 3 standard approaches that you might want to try with experimental type research. The first one would be to quantify training match and demand. So that's something that there's a lot of research there. The limitation, obviously, of that type of research is that it maybe gives you some idea of minimum threshold. So maybe, your player has to have this level of fitness and strength. However, it doesn't really help you with what happens as you start to have higher and higher levels. What additional benefits does that give you? The second standard approach would be something like a rank order comparison. So you would maybe compare, the fitness of elites versus non-elites, youth and adults, maybe losing teams and winning teams, although that would be hard to do because you need to get data across teams and so forth. So this is, again, has been done quite a lot. It gives you some information, but obviously the limitation is that any differences, it's not clear whether those are due to, so differences across the ranks, whether that's due to fitness or whether that's just a byproduct of, for example, age. So, elite players might be slightly older and therefore they've just developed their fitness, or it might be cultural. Elite teams might just enforce fitness, but it doesn't really have much of a additional benefit. Finally, what I think most people would think of as the gold standard would be, a longitudinal tracking. So perhaps we conduct an intervention and then compare performance pre and post. Typically, what we would do with this type of research is we wouldn't use actual soccer performance, we would use proxies. So that might be something like how many sprints a player performed before and after the intervention, average speed, and so on. So proxies take us away from what we're actually interested in. Ultimately, the more complex question is not do they run more, but it's how is the team performance? So do they score more goals? Do they win more? Do they lose more? And obviously that's a complex question to address with an intervention because, if we do we look at tracking some data and then look at something the next season, obviously there's a large number of confounding variables. So what we would need to do is conduct this research over a large number of teams to build up some insight, and that would be challenging to do. And even if we were to do this process, that still gives us insight into only one intervention. So we don't know if our results will generalize to other interventions that perhaps, for example, focus a little bit more on strength and speed and things like that. So an alternative CSM approach would to say, well, we have a system comprising soccer and fitness, and let's choose agent-based modeling, for example. So an agent-based modeling, we might focus on possession. So possession leads to different outcomes. It leads to dribbling, passing, interception, tackling, or shots. And within this model, we parameterize it. So we parameterize it so that our agent-based model maps onto reality. So for example, the number of tackles, passes, goals, etc., match what we observe in elite sport. We can manipulate our parameters to create good teams and bad teams so that goals are more likely to happen at the end of halves and so on. So we can build quite a complex agent-based modeling. And if you think about it, that's kind of what happens in lots of games like FIFA. Those are agent-based modeling, and you can make them very lifelike. But for the purposes of our CSM and this question, what we do is we would incorporate fitness components into our agent-based modeling. So for example, it would be relatively trivial to build a passing model where the success is determined by the location of the pass and the position and top speed of each of the players. So that model building then links our fitness ultimately into performance. Then what we can do is we can manipulate player speed to represent realistic improvements following training. And then we can simulate, for example, thousands and thousands of seasons to quantify the typical improvement in actual performance, such as wins and losses. We can then build more complex models, incorporating changes in strength, improvements in robustness, so for example, reductions in injury probabilities and so on, and get an idea of how physical fitness ultimately influences soccer performance. Now, obviously, I think it's very obvious what the limitations are of this approach and the number of assumptions that are involved. However, I'm hoping what is clear is how different this approach is to traditional research, and that it's certainly creative and at the very least presents a really good opportunity to have some interesting collaborations and interdisciplinary work. Okay, so I'll finish there. So thank you very much.
Awesome. Thank you, Paul. I must admit, when you put the OR codes up, my mind kind of glazes over a little bit, but the rest of it is really interesting. Thank you. I'm thinking, are we better off keeping going, because the next talk is due to start in 3 minutes. And we were supposed to have a short break. I think we're maybe better to just keep going, but Paul has his Twitter handle there. Vanessa just asked if perhaps you can suggest a paper as a basic entry into modeling that maybe we can link to your talk, if there's any resources that you suggest. And that's actually something, guys, we're going to do throughout, is to, when we send you the recordings, we will send links to papers that are mentioned, etc.
Yeah, of course.
Okay, nice. I will stop recording on that. Thanks a million, Paul.